This is our final section of Unit 2, Chapter 6, and we're going to be looking again at equations that you can solve using the skills that you learned in Section 6.3 and 6.5 for factoring polynomials that have special forms. So I've listed the special forms for you again at the top of the sheet. Perfect square trinomials, if you take an a plus a b and multiply it by another a plus b, you're always going to get that first term squared at the beginning, the last term squared at the end, and the two multiplied together and doubled for your middle. Same is true here, except that that sign changes, because when we multiply the b times b times negative b turns positive, but an a times a negative b and another a times a negative b are still going to be negative. Difference of squares, so a perfect square minus another perfect square will always factor into their square roots added and their square roots subtracted. And then the sum and difference of cubes follow a pattern as well that we'll see when we get down into the examples here. So let's start the first problem. This minus 2y plus 72 equals 0. We're going to take that negative 2 off the front since we can factor a 2 out of the 72. And when we remove the negative 2, remember this one needs to change signs, because when you multiply negative 2 times a negative 36, that's what would get us back to a positive 72. So now that we've done that, we're left with the difference of squares patterns, a y squared minus 36. 36 is 6 squared. So to factor that, I can go straight to my two factor pairs with the y's, and I know that it's going to be a 6 and a 6, and that one of them is added and one of them is subtracted. So that leaves me with the answers. There is no way to make negative 2 equal 0, so these are the two pieces of my polynomial that have the potential to be a 0 in order to give us a true answer to this, and those answers are going to be y equals negative 6 and y equals a positive 6. For the second example, we're going to do a little rearranging first to get it into descending order. So I'm going to move that negative 14x squared to the other side. And I see that all three of these equations, or all three of these terms, contain an x. So I have an x that I can pull out of the whole polynomial before I begin my other factoring. So I'll put that x on the outside. That leaves me with x squared minus 14x plus 49 equals 0. And looking at that polynomial, x squared is a perfect square. 49 is also a perfect square. It's 7 times 7. So when I see that constant term being a perfect square, that should set off a warning in your head that, oh, this might be one of these special patterns. So I'm going to look at the 49 and say, well, the square root of 49 is 7. If I take 7 and double it, that's 14. Is that my middle term? And sure enough, it is my middle term. And it's my middle term with a negative sign in front of it. So because of that, this one is following that perfect square trinomial pattern. So I don't have to go through the asking myself what are all the factors of 49 that would add to 14 and all those questions. I can just go straight to the grouping that says that this is going to be x minus 7 twice. So this part set equal to 0 gives me an x equals 0. This one gives me an x equals 7. And this one also gives me an x equals 7. So before, when I've talked about that when you have a degree 3, you can have up to 3 answers This is why I kept saying up to instead of exactly 3, because as you can see with this one, since both of these binomials are the same, they're giving us the same answer for x. So in this case, x is either equal to 0 or 7. Even though it's a degree 3, it only has 2 answers because this answer was repeated twice. Looking at this next example, switch to another color. This is already a linear equation. 2x minus 5 can already be set equal to 0 and solved on its own. So I need to see if there's something I can do with this. So I look at the first term and say, yep, it's a perfect square. It's the same thing as 2x if it was squared. And 25 is also a perfect square. It's the same thing as 5 squared. So that makes me think I might be dealing with a perfect square trinomial case. I'm going to test it by taking that square root and that square root, multiplying them together and doubling them to see if they come up to be the middle. So 5 times 2x gives me 10x, and when I double it, which is what it says to do, take the a times the b and then double it, I do get 20x. So this particular problem follows the perfect square trinomial where all of the operators are positives. So I can go straight to the factoring part and say that this is going to factor into a 2x plus 5 squared, if we want to use the notation that they use there, which means, just like with the example up here, both of those 2x plus 5 terms are going to give me the same answer. So I really only need to find that answer once. So the 2x minus 5 is going to leave me with x equals 5 halves, and the 2x plus 5 is going to leave me with x equals a negative 5 halves. Looking at this next example, 4y cubed equals 36y. I will move the 36y over to the other side. Factor out the y that both of them have in common, which will leave me with 4y. Actually, I can factor out a 4y. So that's going to leave me with just a y squared minus 9 is equal to 0. Once again, 9 is a perfect square, so I have the difference of two squares, difference of y squared minus 9, which is 3 squared. So that's going to factor into y plus 3 and y minus 3. So my three terms here are 4y times y plus 3 times y minus 3, setting each one of those equal to 0, I get y equals 0, y equals negative 3, and y equals 3 as my answers. In the final example, we're looking at x to the 6th minus 81 x squared equals 0. Both of these have an x squared in common that I can take out. When I take out x squared, I'm left with x to the 4th minus 81. And I once again have a difference of squares, because x to the 4th is really x squared squared, and 81 is really 9 squared. So following the difference of squares pattern, I'm going to have x squared plus 9 and x squared minus 9 as my second two terms here. So the x squared that was on the outside will stay, and then I have an x squared plus 9 and an x squared minus 9 equals 0. Okay. This x squared minus 9 is still a difference of squares. So I'm going to factor it one more time into x squared plus 9, and then x plus 3 and x minus 3. So I started with a degree 6, which means that this could have up to 6 answers. So looking at this first one, x squared is equal to 0. That takes care of 2 of my answers. Both of those x's would be zeros. I'm going to skip over this middle one here for a second and go and look at these two, because we already know what to do with those. I have an x plus 3 equaling 0, so that's going to give me an answer of x equals negative 3, and an x minus 3 equaling 0, which is going to give me an answer of x equals positive 3. Now let's take this extra term out here for a second. X squared plus 9 equals 0. And I want you to think for a minute about what happens when you square a number. If we put in 0 in place of our x, we're going to get 9 equals 0, which is not true. If we put in any positive number for x, let's put in a positive 2, when we square it, we're going to get 13 equals 0, which is not true. And even if we try a negative number, a negative 2, when we square negative 2, it turns into a positive 4, which when added to 9 is still going to give us a positive number, which is not equal to 0. So this particular term in our factored polynomial has no way of being set equal to 0, because any number when it gets squared is going to be positive, and when you add more positive to that, there's no way to get yourself back to 0. So these two answers are ones that you're going to deal with when you get to college algebra. So there's 2 answers here that are both zeros, 2 answers here that are imaginary. You'll have to wait to college algebra to solve those. And then there are our remaining 2 answers. So the number of real answers that we got for this equation were x equals 0, negative 3, or 3.